Hey everyone. In the units and dimensions video, we talked about how for any physical equation, if I look at the dimensions of any quantities that are being added, subtracted, or compared, they have to match with each other. We can't compare times in seconds to masses in kilograms or things like that. And also that if we multiply or divide different kinds of physical quantities, their dimensions are likewise multiplied and divided. One of the examples that we looked at was one of these constant acceleration equations. So if I have an object that has the same magnitude of acceleration in the same direction the entire time, so this constant acceleration, we can describe the position of an object at some time t to what is the initial position of that object, what's the initial velocity, what is the constant acceleration that this particle is experiencing, and how much time has passed by. And when we looked at this equation, we found that each of those terms have dimensions of length. The initial position, well, we can think about that as just a length from some chosen origin. Our initial position, just a length. Initial velocity times time, well, velocity is a length divided by a time, and I multiply that by another time, we get length back. 1/2 acceleration times time squared, well, if acceleration is a length divided by a time squared, and we multiply that by time squared, we should get back just units of length, and all of these match up with each other. But we want to be able to put this to the test, and in this video, we're going to specifically look at projectile motion. So what happens if I have an object freely falling just under the influence of gravity, where there is a negligible amount of air resistance and no other forces acting on it? The claim is that if gravity is the only force acting on this object, the acceleration, the value for that acceleration, should be 9.8 meters per second squared, pointing directly downwards. So if we pick up to be the positive direction, this acceleration should be negative. And then this constant acceleration equation that shows again our position as a function of time should follow this form, where I'm replacing the acceleration with this negative g value, this negative 9.8 meters per second squared. So we're going to put to the test both this constant acceleration equation. So when we start looking at some data, does the data actually support that this equation is an accurate way of representing how the position of an object that has a constant acceleration is changing with time? And in the case of free fall motion, do we actually get this little g is equal to 9.8 meters per second squared? So the way that we're going to do this is I completed a number of experiments, 3 specific experiments, where I have a marble going through some kind of free fall motion, either launched from this launcher. So again, I set up this launcher, aimed it directly vertically, and launched it under both low speed and high speed settings, so how launching at different speeds. And an extra trial where I took the marble and used calipers to just drop it at one particular moment in time and have that free fall motion starting from rest. I recorded all of these trials with the slow motion function on my smartphone. So again, this was recorded at 960 frames per second, and identified, put a timestamp on here so we can identify where the marble is at all sorts of different moments in time. The background that I used was this. So I used this as my background. And again, all of these distances are labeled in centimeters just to make sure that everything is above board. If I put this right at the bottom, you should hopefully be able to see that the 70 centimeters, 60 centimeters, 50, 40, 30, all those match up with each other. I tried to make those as reasonably accurate as I could. And some other things that I tried to do was during the setup, oh, that fell over. During the setup, when I was launching this thing, I tried to put the marble launcher as flush against that backboard as possible, so hopefully the camera doesn't give too much of a parallax effect. From the camera's perspective, if the marble is here and the screen is a little bit behind it, I might be kind of seeing a little bit too high when it's further up and a little bit too low when it's further down. But I try to minimize that effect by having the launcher, and when I drop the marble, having that be as flush against the backboard as possible. That might throw off our value by a few percent, but it should be reasonably accurate. So what we're going to be doing is going through this data, and again, these videos, you can look at the full videos, including both the real-time and the slow motion cases. Those are available for you to go through. I do recommend trying the same kind of analysis that I'm going to be doing. I'm going to be picking particular data points. You can try picking other data points, see if we still get the same values. And we're going to look at these videos, analyze this motion, and again, see first if the motion can be described by this kind of quadratic equation. So position is related to time in this quadratic fashion. We get this t squared term. So does that equation describe the motion? And when we try to find what the acceleration of this object is for these projectile motion cases, do we get this negative 9.8 meters per second squared? So let's have a look at things. So again, we're going to be looking at these videos of projectile motion, and I am going to be extracting data from these videos saying at what different times is the particle at different locations. We're going to be graphing that data, saying what are the different times and positions, and I encourage you to follow along with me. I'm definitely not going to do every single frame, partially because that would be a very, very long video, and also because it's not needed. But what we want to get is some data as the marble is on its way up, so maybe 3 or 4 data points while it's on its way up, a few data points when it's near the top of the motion, and a few data points as it's falling back down. And we're going to be graphing this motion and trying to identify, do we get, first, this quadratic pattern, and if we're getting that quadratic equation showing up with matching this data, do we get the acceleration of negative g, negative 9.8 meters per second squared. So again, I encourage you to try it. You can graph in, Excel or Google Sheets. There's lots of different programs that you can use to graph this. But let's just jump into this. So for this video, I set it up so that right when the marble is at 0, that's when the timer starts. We're looking at the top of the marble as our reference point. Again, there's going to be a little bit of error included in this due to the fact that from the camera's perspective, as it's watching the marble with the screen on the background, there is going to be a little bit of a parallax effect that is going to make the motion appear a little bit more exaggerated than we would think. And I'm guessing this is going to give us a slight overestimate for the value of g, but let's see what we get. So again, I'm starting the timer as close to when the top of the marble is at 0, and let's find some data points. So I'm going to move a few frames forwards, and let's say right around there, we're at 5 centimeters. The top of the marble is at the 5 centimeter mark, and our time is 0.229 seconds. So that time is 0.0229 seconds, and our position was 5 centimeters, or 0.5 meters. And basically, we're just gonna kind of scroll through and get a few more data points from this. So there, the top of the marble is around 10 centimeters, and it's at 0.05 seconds. So that's our next data point, and we're basically going to repeat this. So maybe I'll do every 5 centimeters it moves up. So that's 0.791 seconds, it's at 15. And let's go to the next one. So right about there, it's at 20 centimeters. Again, I might be a frame off, a frame ahead, or a frame behind, but that's why we take lots of data during the entire motion. And again, if you think my data points are off, then I encourage you to try this yourself and graph this data and see if you get similar results or dramatically different results. That's why this data is available. So at 0.2 meters, the time is 0.1197. That's 0.2 meters. And let's see if we can get a few more data points. So, looks like it's, don't know if it quite gets to 0.25. Let's say that is going to be 0.24 for the distance. And that time was 0.1708. If we keep moving forward, let's wait till it gets back down to the 0.24 again. So right around here is back to the 0.24, and that is 0.2791. Okay, so notice it's, maybe let's go back a little bit and see if we can get one of those higher data points. So I'll back up a little bit. Say right around there is 0.25, so that's 0.2604. One of the nice things about this is you do not have to put in these numbers in any particular order. Since we're making a scatter plot of this, the order doesn't matter. And let's actually do one of the earlier points. It was 0.25, so right around there looks pretty good. So 1906, yeah, 1906 and 0.25. So we seem to be getting this parabolic arc, but let's keep moving forward a little bit. And as this falls back down, let's pick that as another point. So 0.3312 for the time, 0.2 for the distance. And a couple more points on the way back down. So that's around 0.15 at 0.3729. Sure we got that right. Okay. At the 10 centimeter mark, that is 0.4041. And it's kind of hard to see, but I think that lines up with 5, you know, close enough. 0.4302. Let's scale this so we get the full data set. Move that down just a little bit. So we've gathered this data. And again, I encourage people to try this on their own with their own data points on here. And I want to try to apply a quadratic fit to this. Okay? So if this equation is valid, a quadratic fit should match quite accurately. We should get a very good match when using this quadratic fit. So let's do that. And I would say that is matching up remarkably well. Our correlation is 0.9999, with 1 being it fully matches the data. The amount of error that we're seeing in this between the actual data points and our best fit line is about 0.001, so we're about a millimeter off with this. And it looks like we are matching this quadratic fit very, very accurately. Okay? But what about our measurement for the value of g? We applied this best fit equation, and it gives us, the computer gives us these particular fit parameters, this value for capital A, for capital B, and for capital C. Well, when we're doing this comparison, we have our claimed equation. That position is equal to initial position plus initial velocity times time minus 1/2 what should be 9.8 times time squared. Our best fit equation, slightly rearranged, is going to have a constant term, just this c value, a constant times time, so this capital B times t, plus another constant times t squared, this capital A t squared. So what we can do is try to match up these terms and say, well, the t squared, the constant term in front of the t squared, this capital A, that should match up with negative 1/2 g. Okay? So this capital A value, that should be the negative of 1/2 of the gravitational acceleration. Okay? And in this case, we can say that, just rearrange this and say, well, that means negative 2 times A is equal to our experimental value for little g. Well, our value for A was negative 4.948. And if I multiply that by 2, I get basically 9.90 for our value for the gravitational acceleration. The value for little g that we were expecting was 9.8. We got 9.9 out of this, 9.90. So if we do a percent difference on that, so take the difference between our experimental value of, again, basically 9.9 and the accepted value of 9.8 meters per second squared, that difference divided by the actual value of 9.8, we were within 1% of getting the actual value for this gravitational acceleration. It matches with our particular equation. And remember, we said that for this equation, that acceleration, if we back up a moment, this acceleration, when I multiply it by a times squared, that should give me a position. The units have to be meters per second squared. But there are some other fit parameters in here as well that we might want to analyze. This value for B, if we compare these two equations, our claimed equation and our best fit equation, this value for capital B looks like it should match up with the initial velocity of our marble. Okay? So when we look at this case, it seems that the initial velocity of this marble is around 2.24 meters per second. Now, I don't actually know what this thing launches at, but when we do our high-speed version of it, having a higher launch velocity, this value of B should be substantially higher. What about the value for capital C? Well, capital C should match up with the initial position of this object. And when we set this up, when we went backwards and set this up, we said the very beginning of the motion, when we started this motion, that object was right around position 0. And on this graph, that value of C is really, really close to 0. It's a couple millimeters off based on this fit of all of our data together. So again, we're getting some values that we expect. This value of C, we would expect that to be very close to 0, and it was. This value for capital A, we would expect negative 2 times A to be very close to our value for the gravitational acceleration. We were expecting 9.8 meters per second squared for the gravitational acceleration. We got 9.9 meters per second squared. Within 1%, the error was only off by less than 1%. But let's try another case where we have the higher velocity marble launch. So let's redo this experiment. So here we're going to be analyzing the motion from the high velocity marble launcher trial. Again, this video is available online. You can go through the data for this yourself. I encourage it. Try the analysis yourself. And this time, we're still using the top of the marble as our reference point. Unfortunately, just due to how long the slow motion video is available, how much slow motion video, right at the end here, we do kind of lose the last little downward part, but we're still going to try to get a few data points while it's on the way up, a few data points while it's near the top, and a few data points as it's on its way down. And again, the only difference here is we are launching this thing at a higher initial velocity. So the value that we get for capital B should be larger than what we had before, but we should still get the same quadratic equation fitting very well, and the same value for capital A, something very close to the negative of 1/2 times 9.8 meters per second squared. I'm going to be taking more data this time, so I think I'm probably just going to speed this one up. I'll just do some of the first data points here. So let's kind of move ahead to right around here. The top of the marble is at 5 centimeters, and the time is 0.0135. And again, the rest of the data points we're going to do the same kind of way, so I'm going to speed up this part of the video. Okay, so this was the data that I got, and that was the last frame that I was able to get. Again, the slow motion video cut out before it got all the way back down to the bottom. But we get this particular shape out of this, and let's see how it matches with a quadratic fit. Okay. So when I match up that data, again, our correlation is essentially 1. And our root mean squared error, like how far each of these points are from this one best fit parabola, is off by just a little over a millimeter. What about the other values? So we said our experimental value for the value of little g should be the negative of twice this value, so 4.934 times 2. Again, cancel out the negative sign. I get 9.87 meters per second squared. When the actual value, the accepted value, would be 9.80 meters per second squared. And the percent difference between those, less than 1%. Even though we were launching this thing at a very, very different speed, it got a lot higher up during that motion, we can still measure this value of little g to a high accuracy. Also notice this value for capital B. We said that should be the initial velocity. This initial velocity is a lot higher than what we had, if I can bring this one over, than what we had for our first case. This one was a lower initial velocity. This one was a significantly higher initial velocity. But we got that matching between our of if this is launching at a higher velocity, it shouldn't change the values of A and C very significantly, but it should significantly change that value for capital B. The value for C, again, at the beginning of the motion, this is very close to being at position 0. So this, again, supports both this model that my constant acceleration equation is correct. You know, position will change quadratically with time. It'll make a parabola. And that we are able to use this parabola and the best fit to our data to identify to a high precision what this value of little g is equal to. And we get, again, very close to that 9.8 meters per second squared. So let's look at one more case where I do the dropped marble test. Instead of launching this thing up, I'm going to do the video where I just drop the marble from rest. So again, for this case, I was using calipers to drop it at a particular moment in time. It was a little bit difficult to identify when was the first frame that the marble was starting to move because the initial velocity is 0, so it's hard to tell what might be a little bit of motion in my hand and what's the actual drop. So I might be a few frames off on the start, either ahead or behind. That's going to correspond with being off by a few milliseconds, and when we look at the entire motion of this thing, that shouldn't throw off our numbers too much. Hopefully we should still be in a pretty good ballpark. Also note that I'm going to be using the bottom of the marble as my reference point in this case, since we can see that the bottom of the marble is just a little bit above 0.74 meters at the beginning of this motion. The rest of this is going to be analyzed in the exact same way that we were looking at some of these other cases, saying I'm going to map out at what particular times the marble is at different positions. And again, I encourage people to look at the raw data. Again, it's posted online, and try to do a similar analysis, you know, see if I'm picking the right points. I'm probably going to show just me picking 1 or 2 points and then accelerate it through the rest of it so I'm not using up too much time. But let's look at the first couple parts. So let's go to the 70 centimeter point. So right when the bottom of the ball is at 70 centimeters, that time is 0.0875. Position is 0.7. And again, we're basically going to be going through these different cases in the same kind of way. So moving to 0.65 centimeters, we've got our time of 1.312. Sorry, 0.1312. And let's just take a whole bunch more of these measurements. Okay, so again, we've gathered the data in the same way, going through this and looking at, again, the reference point for my data here is the bottom of the marble. You can use the top of the marble and try to reproduce the experiment. So let's see what happens when we apply our quadratic fit. So again, the prediction is that the value of A should still give us a fairly accurate measurement for the value of G. And this one should have been released from rest, so the value of B should be around 0. And the value of C, the initial position, that should be around 0.74. So if we try our fit and hit OK for this one, well, let's see how close we got. Well, for our value of B, we got something fairly close to 0. Again, exactly identifying, did I pick exactly the right frame as our starting point? Looks like I was a little bit off, but, you know, pretty much in the bounds of error. For our initial value for C, again, this could be part of the parallax effect, throwing our numbers off, but pretty close to 0.74 centimeters. And our acceleration, well, if I multiply this by -2, then I'm going to get, well, I get 10.4. A little bit further off than what we had for some of our other measurements, but if I do the percent difference, so again, the 9.8 is the expected value, subtract our 10.4 for the experimental value, and then divide by the true value of 9.8, I'm within about 6% of the accepted value. So again, fairly close matching between these two experiments. And I think since we didn't do an up and down version, those parallax effects kind of threw the numbers all in one particular direction. So that could be why we're getting a little bit of a higher percentage on our errors for this one. But again, we're still in fairly good agreement with these particular cases. So again, we've gone through a number of different cases of analyzing this data, of analyzing cases where marbles were launched in the air at different speeds, cases where I dropped the marble from rest or pretty close to rest, and it seems to match up with, again, both the claim that this is our equation for constant acceleration motion, and that the value of G should be 9.8 meters per second squared in order to get the units for this case to work out. But maybe you think that, you know, this method of fitting the data, it's playing a little bit fast and loose with how we're identifying the units. Again, my argument before was that the units, the dimensions of these quantities, always have to match up if we are adding, subtracting, or comparing quantities. So if this equation is correct, which our data strongly supports that equation being correct, again, in this case, we had very small amounts of errors for this general parabola fit. And in order for this to work, the acceleration, when I multiply it by a times squared, by seconds squared, I have to get back a unit of length, meters. So the acceleration has to be meters per second squared. But again, maybe you're not convinced by this. So instead, let's look at another way of trying to analyze the same data for this free fall drop from rest. Okay. Again, if we're looking at the specific drop from rest case where the initial velocity was essentially 0, well, if that initial velocity is 0, then in this equation, this term goes away, and I can rearrange this pretty simply to solve for the value of little g. And if this equation is right, g should be equal to 2 times the initial position minus the final position, divided by the time squared, the time for that fall squared. Again, this only works if the object is starting from rest, and this little x0, that is our initial position, which again, we said in this case was around 0.74 meters. So I've set up an Excel sheet to try to do this calculation for us. We're going to use the exact same data that we had down here, the exact same data that we gathered, and say, well, my initial position, it really looked like it was around 0.74 for that initial position. And then I can put in all of the positions that I had at different times. And what this spreadsheet will do is it will calculate first what is my initial position minus my final position. So again, it's this initial position, cell B1 right here, minus my final position, the corresponding A cell for this row. And then our experimental value for G, just using this equation, is going to be 2 times this cell divided by my time squared. So we're literally doing a change in position, how much the position has changed, times 2. Again, 2 doesn't have any units associated with it. But we have that change in position in meters divided by the time that that takes in seconds squared. We are squaring that value. So let's see what we get. And again, this one is going to be our position. This one here is going to be our time. So let's make sure that we don't get those two columns mixed up. So this first position was 0.7 meters and the time was 0.0875. And already we're matching up to within a few percent, 6 or 7% error. But let's see how things go as we change some of these values. So there we're still around 6%. So again, we might have actually had a little bit of error with this first point. Like if I make this a little bit smaller, we actually might get some better percent error, but let's just go with the numbers that we have right here. So notice that for all of these, when I do my positions, my change in position times 2 divided by the time squared, we're getting things that are, again, a little bit higher. Sorry, this one I actually typed in the wrong thing, so let me correct that one. Okay, so we seem to have some kind of small systematic error that's throwing our numbers off by all around 5%. But we're still in pretty good agreement with the value of G. It should be 9.8 meters per second squared. We're getting a little bit over 10 for most of these. And again, as we go to the lower values, it's getting a little bit better. It's still going to be around 5% off in this case. But again, we got these results by looking at a change in position in meters, again, still times 2, divided by the time squared. The units for all of these are going to be meters per second squared. And just for comparison, let's say I try to switch this around and take out the squared value. So let's say I take out that squared value. Notice all of these numbers are going to be really, really different from each other. If I don't have that time squared value, when I go to these different times, not only do we not get the same value showing up, the values are all different for each one of those different changes in times. We have to use the squared value in order to get this, reasonably accurate measurement of the value of G. Again, within 5 to 6% seems to be what we're going with for this particular one. But again, things like that parallax effect, saying I'm slightly overestimating the distances up here and slightly underestimating the distances down here, that actually is going to have the effect of making it look like the acceleration is greater than it actually is. It's kind of magnifying that scale. So that would be my guess as to where most of this error is coming from. Just to close this off, again, the point of all this is that when we make these different kinds of measurements, we need to keep track of what kind of units we're using for this. Okay? In this case, whether we use our method of using the best fit equation and matching up the parameters in our constant acceleration equation, we're going to get that these accelerations have to be in meters per second squared in order for the units to make sense. Otherwise, we're going to be trying to compare units, trying to add or subtract and compare units that are not commensurate with each other. Saying things like, this many meters equals this many seconds, or this many kilograms equals this many newtons, or something like that. They are not the same kinds of quantities, and we have to treat them differently, because if I'm trying to compare quantities that do not have the same units, we get nonsense results. We can't say that, oh, this many meters is equal to this many kilograms. It just doesn't make sense. And again, whether we use the constant acceleration equation and compare that with our best fit equations, or we look at the data points individually and say, well, we can get a decent estimate. Again, it was a little bit higher error than I was hoping for, but we get a pretty decent estimate for this value of little g by looking at 2 times that change in position in meters divided by the time in seconds squared. We're having to square that time in order to get these values. We're going to be looking at more cases of how do we look at the units of different kinds of quantities, how do we use that to our advantage in dimensional analysis, other independent ways of measuring the value of little g. So we're going to look at another experiment where we have a separate way of measuring little g by looking at the motions of pendulums. And also, we're still going to find that the units have to be meters per second squared. So those will be some of the topics in future videos. As always, if you have questions, throw those questions into the comments. I try to answer those, and please be kind and courteous to other people who are asking questions as well. And thank you for your attention.